Part H, Graphical Transformations. Before we take a look at a few examples, review those rules in your packet for how to transform functions. If we add a number after our function, it will move the function up, and if we subtract a number, it will move it down. If we subtract a number inside our function, it will move it to the right. If we add a number inside, it will move it to the left. If we multiply our function by a number, it will stretch the function by a factor of that number. We'll multiply the y values by that number. If we multiply our function inside by a number, it will compress the function horizontally by the factor of that number, so we'll divide all the x values by that number. If we look at y equals f of negative x, that would be a reflection over the y-axis. If we look at y equals negative f of x, that will be a reflection over the x-axis. And if we apply negatives in both places, it will be a reflection over the origin, really a rotation about the origin 180 degrees. Really, though, we can just think about it as a reflection over the x and y axes. The first example we're going to look at is sketching f of x equals x minus 3 to the third minus 2. What we need to do is figure out, based on the function we're given, what the parent function will be. Then we'll apply our various transformations to that. Well, looking at this function, because of that cube, that will make my parent function just f of x equals x to the third. And I'm going to plot that. 0, 0, 1, 1, 2, 8, negative 1, negative 1, negative 2, negative 8. Connect the dots, and that's our parent function. We then have our transformations to apply, and the way I'm going to do this is just one transformation at a time. If you had me for Algebra 2, you saw transformations this way. And sometimes the order that we go in will matter, other times it won't. The order we should go in is if we were plugging a number into our original function, into that original x minus 3 to the third minus 2. What would we do first? What would we do second? And so on. And the first thing we would do is the first transformation we should apply. So what I mean by that is, if I was plugging in a number to that original function that I'm trying to graph in the end, the first thing I would do to it is subtract a 3. Well, that's the first transformation I should apply. I should take my parent function, and I should deal with that minus 3. Well, a minus 3 inside our function moves it right 3 units. So I'm just going to take all my points and go right 3 units. I'm going to do multiple graphs on a single grid just so I really see what's going on. You're certainly welcome to do this and to use different colors if that helps you keep your transformation straight. Well, after plugging in a number and subtracting 3, I would cube it. Well, that just gave me the parent function, so that doesn't do anything for me. But then, that minus 2 at the end is the next and final transformation I need to apply. That minus 2 after my function will take that graph I just did, that green graph, and move all the points down 2 units. This point moved down 2 will be over there, and there, and there, and there, and there, connecting the dots. This black graph that I'm drawing right now is my final graph. Make sure if you do put multiple graphs on a single grid, you very clearly indicate what each graph represents and which one is your final one. Next example. Let's take a look at f of x equals 3 times the square root of negative x. Well, my parent function here is just the square root function, so I'm going to start by graphing my parent f of x equals root x. 0, 0, 1, 1, 4, 2, 9, 3. It's my top half of a sideways parabola. If we were going to plug a number into this thing, the first thing we would do is that negative. That negative inside is the first transformation that I need to apply. A negative inside my function is a reflection over the y-axis. So that will reflect over the y-axis. So after that reflection, my graph looks something like this. And finally, I have that 3 out front. that 3 is a vertical stretch by a factor of 3. And what that means is I need to take all the y values on my green graph and multiply them all by 3. That 3 is a vertical stretch by a factor of 3. So, this point had a y value of 0, the y value is still 0. This point had a y value of 1, the new y value is 1 times 3, or 3. Y value here was 2, my new y value is 6. Y value here is 3, the new y value is 9. My final graph is that black one that I just sketched. Next, let's take a look at f of x equals -1 over x plus 4. Well, my parent function here should be f of x equals 1 over x. So I'll start from that. Remember, that's the graph with the vertical asymptote on the y-axis and a horizontal asymptote on the x-axis. And then I have points at 1, 1, 2, 1/2, 3, 1/3, 4, 1/4, 1/2, comma 2, 1/3, comma 3, and so on. Same in quadrant 3. The first transformation I need to apply is that plus 4 that's in the denominator. Well, that plus 4 is inside the function, so it's a horizontal shift. Plus 4 will take your parent function and move it left 4 units. Notice that when we do this, it will also move our vertical asymptote left 4 units. So I'm going to start actually by moving that asymptote. My horizontal asymptote will still stay on the x-axis, and moving everything left 4, I get 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and so on, connecting dots. I get something like this. Finally, that negative out front will be a reflection over the x-axis. Reflect over the x-axis. I'm going to keep my asymptotes where they are, and I'm just going to flip all the points over the x-axis. And that black graph is my final one. Two more that I'd like to look at. On the next page in your notes, you're given the graph of some function, f of x, that I'm going to copy over here. F of x had points at -4, 1, -1, 3, 2, -1, and 4, 0. So rather than using a parent function, well, one of our 13 basic graphs is our parent function, we're going to use this graph drawn, f of x, as our parent function. And we are asked to sketch y equals -f of x minus 2. Well, I'll apply the transformations in the same way that I dealt with before. If I was plugging into this, the first thing I would do is subtract 2 from any x value. So that's the first thing I want to sketch, f of x minus 2. A minus 2 inside my function will move it right 2 units. So moving all the points right 2, I get something like this. Then that negative out front will flip my function over the x-axis. This point was 1 above, it's now 1 below. This point was 3 above, it's now 3 below. This point was 1 below, it's now 1 above. This point was right on the x-axis, so it stays there. That blue graph is my final graph. That's the sketch of y equals -f of x minus 2. One more of these. Again, we're going to start from f of x which has points at negative 4, comma 1, negative 1, comma 3, 2, comma negative 1, and 4, comma 0. And we are asked to sketch y equals 2 times f of negative x plus 1. If we were going to plug in an x value, the first thing we would do is change its sign. So I'm going to start by dealing with f of negative x, which is a reflection over the y-axis. This point was 4 to the left of the y-axis, it's now 4 to the right. This was 1 to the left, it's now 1 to the right. This point was 2 to the right, now it's 2 to the left. This point was 4 to the right, it's now 4 to the left. After my reflection over the y-axis, the graph should look like this green thing. If I was plugging in a number, I'd first change the sign, then apply the f function to it. The next thing I would have to do is multiply that answer by 2. That 2 is the next transformation I need to apply. That's going to be a vertical stretch by a factor of 2, so I need to multiply my y values by 2. This y value is 0, the new y value is 0 times 2, still 0. This y value is negative 1, the new y value is negative 1 times 2, or negative 2. This y value is 3, the new y value is 3 times 2, or 6. This y value is 1, new y value, 1 times 2, or 2. Finally, I need to deal with that plus 1 at the end, which will just take my graph and move everything up 1 unit. So up 1, up 1, up 1, up 1. And that magenta graph is the final one.